At this very moment, within this immense galaxy, an intelligent civilization could be gazing at the heavens, pondering the existence of others. They might possess cities and advanced technology. They might even have star-faring vessels, yet it's inconsequential, even if a million civilizations are dispersed throughout the Milky Way right now. The fundamental laws of physics have constructed a confinement around each and every one of them. Not a confinement of rudimentary engineering, but one of vast distances, quantifiable in light years. This confinement is also composed of energy, intrinsically woven into the principles of relativity and of time, which inevitably obliterates all structures in societies. The point here isn't about the existence of extraterrestrials. Instead, it concerns the reasons why the cosmos itself renders it practically unfeasible for any such civilization to ever arrive on Earth. The true obstacle isn't a lack of intelligence. It's the very nature of reality. If you wish to grasp the singular argument regarding alien existence that is rarely discussed, the argument founded not on conjecture but on pure physics, please take a moment to like this video, and then we shall commence. Observe the night sky on a cloudless evening. Locate two stars that seem to be almost adjacent, practically in contact, resembling a pair of luminous points affixed to dark velvet. Your vision suggests their proximity. Your mind readily accepts this perception, viewing an overhead dome, a surface dotted with points of light. This constitutes the initial error. Those two particular stars could actually be separated by many dozens of light years. One might be comparatively close, perhaps a red dwarf merely a few light years distant, while the other could be hundreds of light years away. This distant star might be a colossal blue giant blazing far beyond the first. Their apparent closeness is solely due to your visual perception flattening three-dimensional depth into a two-dimensional image. The night sky isn't a physical ceiling. It's not a mere surface, rather, it's an immense three-dimensional expanse so vast that your visual apparatus is incapable of processing it precisely. Evolution equipped the human brain to gauge distances. This capability extended to judging distances across woodlands, over plains, and along rivers. However, it did not equip us to comprehend distances quantified in trillions of miles. Consequently, the mind simplifies and flattens this information, transforming the unfathomable into something comprehensible. This perceptual flattening poses no harm when you're estimating the distance to a tree. Yet, it proves disastrous when attempting to estimate the distance to a star. The closest stellar system beyond our own sun is Alpha Centauri, situated roughly 4.24 light-years away. This figure seems insignificant and fits comfortably within a single sentence. However, a light-year is far from an ordinary unit. It represents the distance light traverses over the course of 1 year. Traveling at approximately 670 million miles per hour, a single light-year amounts to almost 6 trillion miles. If you multiply that by 4.24, the closest star is positioned approximately 25 trillion miles from Earth. Should you try to count to 25 trillion, enunciating one number every second without interruption, it would require almost 800,000 years to complete. Your counting would commence. You would have started long before the construction of the earliest cities, and whole civilizations would emerge and vanish before you arrived at the ultimate figure. That is the actual distance to the nearest star. This isn't a star located on the opposite side of the galaxy, nor an unusual celestial body at the boundary of the observable universe. It's simply the closest one. Human intuition utterly falters when confronted with this magnitude, since nothing in our daily routines equips us for it. The Pacific Ocean, measuring around 11,000 miles across, feels immense, however. That particular distance would fit into the space between Earth and Alpha Centauri more than 2 billion times. If you lined up 2 billion Pacific Oceans, you still wouldn't get there. Alpha Centauri is thought of as close. Go a little further out, and the distances quickly become much larger. The shining star Sirius is 8.6 light-years away, and Vega is about 25 light-years distant. These are stars observable with the unaided eye, presenting as mere dots in the identical sky, despite being separated by distances that would demand tens of thousands of years to cover, even at the speed of our fastest spacecraft. The Milky Way galaxy itself extends for roughly 100,000 light-years from one side to the other. The fastest phenomenon in the universe, light, takes 100,000 years to accomplish that trip. Not a vessel, not a probe, but light. When individuals envision alien civilizations visiting Earth, they infrequently consider the true location of those civilizations. They envision close neighbors and voyages much like long trips on Earth. Hard, but possible if one is determined enough. However, stars are not positioned like cities along a coastline. They are dispersed throughout a spatial volume so immense that even adjacent stars are separated by trillions of miles of empty void. The mean distance between stars in our galactic vicinity is around 4 to 5 light-years. This means every star resides within a sphere of void that is several trillion miles in diameter. Prior to encountering the subsequent one, visualize compressing the entire Milky Way to the scale of the continental United States. At that proportion, each star is akin to a grain of sand. The closest grain might be located a few inches distant. The next promising grain, potentially harboring a habitable world, could be many yards away. Civilizations separated by thousands of light-years would be divided by distances comparable to traversing whole states. The greater part of the map would be empty. This void is not poetic, it is purely geometric. The galaxy contains hundreds of billions of stars. However, it also encompasses an immeasurable quantity of space between them. The density is minimal, the distances are vast. Even if intelligent life emerges around numerous stars, the mean separation between civilizations would likely be counted in hundreds or thousands of light-years. Assume with optimism that 1 in every million stars supports an intelligent civilization. The Milky Way contains approximately 400 billion stars, which would imply perhaps 400,000 civilizations distributed across the galaxy. That quantity sounds vast, but if those civilizations are spread uniformly through a disk 100,000 light-years in diameter and thousands of light-years deep, the mean distance between adjacent civilizations becomes immense. Not 4 light-years, not 10, but more likely hundreds or beyond. The geometry is the primary factor. This is where the deceptive nature of the night sky becomes hazardous. When gazing skyward, we perceive luminosity lacking depth and points devoid of volume. We mistakenly infer closeness where none truly exists. Stars seem within reach simply because they look near. However, their apparent nearness is merely an illusion, a product of our restricted human vision. All hypotheses concerning extraterrestrial visits stem from this very misperception. This starts with the notion that stars represent destinations, reachable through lengthy yet feasible voyages, akin to islands scattered across an ocean that a highly advanced vessel could traverse. The truth is far more severe. The void separating stars isn't an ocean teeming with currents and breezes. Instead, it's a vacuum so absolute that on average it holds approximately 1 atom per cubic centimeter. To put this in perspective, the air you inhale contains roughly 25 quintillion molecules within each cubic centimeter. The space between stars is unfathomably less dense than our planet's atmosphere by trillions upon trillions of times. It's virtually empty, and this emptiness extends for light-years. Spanning in all directions, moving from one star to another isn't like journeying across land. It's navigating sheer emptiness. There are no intermediate stops, no places to refuel. There are no inherent stepping stones, only distances measured in trillions of miles, and distance offers no compromise. Should an extraterrestrial civilization inhabit a star, located 500 light-years distant, then even light itself would take 5 centuries to reach us from their location. A spacecraft moving at a mere fraction of light's velocity would necessitate thousands of years for the journey. Expanding this further, a civilization situated 5,000 light-years away would demand 50,000 years to reach at 10% of light speed. These figures are not theoretical, they are direct results of geometric principles. The galaxy isn't a local area, it's more like an archipelago, where every star stands as a solitary island, encircled by vast expanses of vacuum. Even if a civilization is highly developed, even if it commands technology vastly superior to our own, it cannot shrink the galaxy, nor can it relocate its star nearer to ours. It's unable to alter the fundamental arrangement of the Milky Way. Distance represents the primary barrier. Prior to contemplating propulsion methods, energy sources, or engineering constraints, we are compelled to face the sheer magnitude of the scale itself. For once you genuinely grasp the immense distances at play, once you substitute the deceptive flat dome perception with the actual three-dimensional reality, the entire discussion transforms. It ceases to be a matter of mere curiosity or imaginative speculation. Instead, it evolves into an inquiry about whether any civilization, regardless of its location, can realistically bridge chasms measured not in miles, nor in millions of miles, but in trillions upon trillions of miles. And this is just the initial point. Distance alone doesn't render something unachievable. One can traverse an ocean given sufficient willingness to journey. You can orbit a planet if you possess the necessary stamina. In theory, you could even passively travel between stars, provided you are prepared to wait for tens of thousands of years. However, there's a specific reason why serious deliberations regarding interstellar travel don't center on passive drifting. They prioritize velocity. This is because the sole method to shorten a voyage from geological time frames to a duration compatible with a civilization's existence is through speed, and speed alone. Traversing interstellar distances incurs such a severe energy cost that it converts what would otherwise be a minor inconvenience into an impassable barrier. To comprehend this, let's commence with a modest scenario. Envision a robotic probe, approximately 1,000 kilograms in mass, comparable to a compact automobile, devoid of a crew or life support. There's no artificial gravity, merely instrumentation, a power supply, a communication network, and a structural chassis. Now pose a straightforward inquiry. What quantity of energy is required to propel that probe to 1/10 the velocity of light? This speed, equivalent to 10% of light's velocity, measures roughly 30,000 kilometers per second. At such a velocity, one could traverse the distance from Earth to the Moon in less than 13 seconds. This appears swift, and it truly is, but even when traveling at 10% of light speed, the closest stellar system, Alpha Centauri, remains over 4 decades away. The kinetic energy necessary to accelerate a 1,000 kilogram probe to that particular velocity amounts to roughly 4.5 or 10 or 17 joules. This figure conveys minimal meaning in isolation, so let's juxtapose it with a more familiar reference point: a sizable nuclear power facility typically generates around 1 gigawatt of power throughout a full year. That specific plant produces approximately 310⁻16 joules of energy. Propelling our compact probe to 10% of light speed would necessitate over a decade of that plant's entire energy output, exclusively dedicated to a singular launch. Furthermore, that calculation only covers acceleration. Should you desire the probe to decelerate upon reaching its intended destination rather than merely hurtling past the star within a few hours, an equivalent amount of energy must be supplied for braking. The total energy expenditure consequently doubles. Now consider augmenting the mass. Swap out the compact probe for a craft capable of transporting even a minimal crew, incorporate radiation protection, life support apparatus, structural fortification, navigation components, communication arrays, and redundant systems. The mass would then surge from 1,000 kilograms to potentially hundreds of thousands or even millions. The energy demand is directly proportional to mass. Amplify the mass by a factor of 1,000, and you simultaneously amplify the energy requirement by 1,000. This phenomenon is not indicative of technological inefficiency. It is a dictate of physics. Kinetic energy escalates with the square of an object's velocity, thus doubling the speed results in a fourfold increase in the necessary energy. As one approaches the speed of light, relativistic phenomena begin to exert their primary influence. The object's effective mass expands. Each subsequent increment of velocity necessitates a disproportionately greater amount of energy compared to the preceding one. At 90% of light speed, The energy demand is not simply 9 times greater than at 30%, it is substantially more. At 99%, it reaches an extreme magnitude, and at 100%, it becomes boundless. That particular term is not employed rhetorically. According to the tenets of special relativity, accelerating any massive object to the speed of light would demand an infinite amount of energy. An infinite energy supply is impossible to generate. Chemical rockets are instantly disqualified as their exhaust velocities are excessively low. The rocket equation guarantees that propellant requirements escalate exponentially with the desired velocity. Attaining even a minuscule fraction of light speed through chemical propulsion would consume more propellant than is present on Earth. While fission offers a minor improvement and fusion enhances it more, neither alters the basic connection between mass, velocity, and energy. They merely offer more potent methods for settling the identical cost. Even antimatter, which is the most energy-rich fuel conceivable, fails to eliminate the expense. The annihilation of matter and antimatter transforms mass directly into energy, as per Einstein's formula. EMC2. This represents the most efficient reaction permitted by physics, yet it remains insufficient to render interstellar journeys effortless. Propelling even a moderately sized spacecraft to a substantial fraction of light speed with antimatter would necessitate amounts vastly exceeding anything mankind has ever created. Indeed, the entire quantity of antimatter ever generated in labs totals less than a speck of dust. Manufacturing even 1 gram would demand immense resources. If one scales that up to the hundreds or thousands of kilograms needed for a viable interstellar voyage, the figures become so astronomical that they move beyond the realm of practical consideration. Some suggest external propulsion techniques to circumvent the requirement for internal fuel. Laser-powered light sails serve as an illustration. An array of potent lasers projects energy onto a reflective sail, propelling the vessel onward without it needing to carry its own fuel. Theoretically, this eliminates the exponential cost associated with the rocket equation. However, in reality, it presents a distinct obstacle. To accelerate, even a probe weighing mere grams to a fraction of light speed would necessitate laser arrays generating power equivalent to the total electrical production of whole countries. Furthermore, such a setup can only provide thrust. It cannot slow the craft down upon arrival at its destination, unless another laser array of comparable size has already been built at that location. This, of course, presupposes that someone has already completed the trip. Every propulsion concept, upon careful scrutiny, leads to the identical conclusion. Interstellar journeys require energy outlays that are not simply vast, but are on a civilization-wide scale. Moreover, energy isn't solely about its presence, it's about its distribution. Even a very advanced civilization, one able to utilize the complete energy output of its star, what physicists term a Type II civilization on the Kardashev scale, has to determine how to allocate that immense power, fueling urban centers, supporting ecological systems, operating computing networks, and upholding infrastructure. Redirecting a substantial portion of a star's energy to propel a single spacecraft for decades is far from insignificant. Even at that magnitude, it signifies a dedication, akin to reallocating planetary resources towards a solitary endeavor without any assurance of success. And this applies to just one mission: to explore methodically. Visiting scores or hundreds of stellar systems would repeatedly amplify that energy requirement. Crucially, increased energy does not modify the fundamental speed limit. It fails to eliminate relativistic limitations, nor does it shrink the galaxy. Instead, it merely enables one to settle the identical, non-negotiable cost with greater ease. The principles governing movement do not yield for intellect. An extraterrestrial civilization, millions of years our senior, still confronts identical equations. They are capable of enhancing efficiency and minimizing waste, but they cannot diminish the baseline energy needed to propel a specific mass at a particular velocity. That minimum value is immutable. Its value is dictated by the spacecraft's mass and the velocity of light. No engineering advancement modifies this correlation, nor does any innovation reduce it beneath the physical threshold. This represents the second barrier. Distance dictates the extent of their required journey, and energy determines if they can achieve sufficient speed for it to be significant. And upon merging these two elements, when one computes the energy necessary to traverse hundreds or thousands of light years within the lifespan of a civilization, you encounter figures that do not merely test engineering capabilities, they challenge the very feasibility of the concept, because interstellar travel is more than just a voyage. It constitutes an energy exchange on a scale so immense that it strains even the conceptual capacity of advanced civilizations, and the cosmos offers no price reductions. Envision that the engineering obstacles have been surmounted, the resources collected, the vessel constructed, and accelerated to a significant portion of light's velocity. The home star recedes behind it, while the destination star remains a remote point ahead. Now, the primary limiting factor is no longer distance. It is the passage of time. At 1/10 the speed of light, the closest stellar system, Alpha Centauri, is over 4 decades away. That constitutes the nearest achievable objective. A civilization located slightly further, 100 light-years away, would necessitate a journey spanning 1,000 years. At 500 light-years, the duration of travel extends to 5,000 years. For a distance of 1,000 light-years, 10 millennia pass before arrival, 10,000 years ago on Earth. Written communication had not yet developed. The most ancient surviving monuments today are more recent than that era. Entire languages have both emerged and faded away within significantly shorter periods. No civilization known to us has maintained cultural or political stability across such vast intervals. Institutions fragment, governments fail. Scientific understanding is both forgotten and subsequently rediscovered. An interstellar voyage spanning millennia must persist for a longer duration than the society that launched it has likely ever existed. A proposed solution is the generation ship, an immense, self-contained habitat carrying a population large enough to procreate and preserve genetic diversity over centuries. The initial crew would not reach the destination, their progeny would. Yet sustaining a closed ecosystem for thousands of years is not merely an incremental advancement of current space travel. It represents an entirely distinct category of challenge. Every molecule of oxygen must be recycled. Each drop of water must be purified and indefinitely reused. Agricultural systems must operate continuously without seasonal resets, lacking soil replenishment from planetary cycles and without external contributions. Even on Earth, with its gravity, sunlight, and the stabilizing influence of a planetary biosphere, completely self-contained ecological setups have found it challenging to maintain equilibrium beyond brief test durations as minor chemical discrepancies build up. Microbial communities fluctuate. If such a system operates for centuries in a harsh vacuum, subjected to radiation without outside intervention, the likelihood of breakdown consistently increases. Mechanical components introduce an additional vulnerability. Metals experience fatigue, seals deteriorate, and electronics incur radiation harm at the atomic level, meaning even exceptionally dependable parts ultimately cease to function. When subjected to continuous strain, the mathematics of reliability are relentless. A system possessing a 99.9% annual survival probability nonetheless confronts formidable chances of failing over 10,000 successive years. If one multiplies that hazard across thousands of interconnected systems, the likelihood of continuous functionality near zero. While duplication mitigates danger, it also adds weight. Greater mass necessitates more propulsion, and higher propulsion requirements lead to increased system intricacy. Intricacy creates fresh points of vulnerability. The difficulties intensify instead of negating each other. Beyond biological and mechanical aspects, sociology comes into play. A community restricted to a spacecraft for many generations would develop in seclusion. Cultural divergence would be inevitable, and the objective of the mission would transform as recollections of the home planet, recede into the annals of time. Offspring born on the vessel would not perceive the initial journey as a personal sacrifice. For them, the spacecraft would represent their normal existence. The target star would not signify a return home. Rather, it would be an abstract instruction passed down from individuals who perished long ago. Governmental frameworks would undergo alterations. Leadership would navigate periods of crisis and restructuring. Disputes would emerge concerning resources, beliefs, and power. The course of human history illustrates that, even with stable global circumstances, societies seldom maintain unity for prolonged durations. A generation ship intensifies these strains. There are no outside commercial partners, no influx of new residents, no territorial growth. Population figures must be meticulously managed. A food shortage resulting from an agricultural failure is not confined to one area. It affects the entire vessel. Over hundreds of years, the mental burden of mere confinement grows substantial. Furthermore, the passage of time diminishes ties to the originating culture. A journey spanning 1,000 light-years at 1/10 the speed of light demands 10,000 years for completion. Throughout that period, the civilization that initiated the mission keeps evolving. Technologies progress, cultural norms transform, and whole species might modify their biology via natural selection or genetic manipulation. The society responsible for dispatching the mission could disintegrate, assimilate into a novel entity, or vanish completely. By the moment the voyagers reach their destination, they embody a form of their civilization that has ceased to exist. Communication fails to close this divide. Signals propagate at the speed of light, meaning a message transmitted over 1,000 light-years requires 1,000 years to reach its recipient. A response necessitates an additional millennium. Each back-and-forth interaction covers 2,000 years. At such a magnitude, meaningful conversation is practically unfeasible. Engineering advancements, governmental mandates, even basic comforting words would arrive centuries past their utility. The spacecraft gains independence from the instant communication delays, surpass any practical significance. Relativistic time dilation offers partial relief to voyagers. At speeds nearing light, time progresses more slowly aboard their craft. Relative to stationary observers, a crew traveling at 90% of light speed experiences time at less than half the rate of those remaining at rest. However, significant time dilation necessitates extreme velocities, and such extreme speeds demand immense energy, especially as one approaches light speed. The energy curve becomes steeper. Time dilation reduces the subjective duration of travel while dramatically increasing the energy barrier, yet it does not eliminate the millennia experienced by the originating civilization. An additional complication arises from technological advancements themselves, particularly if propulsion improves over time. Any mission launched today risks being surpassed by a swifter mission initiated centuries later. Rational planning suggests waiting for superior technology. But indefinite postponement means no mission ever departs. This creates a paradox: launch now and risk obsolescence, or delay and postpone indefinitely. Even self-replicating probes, machines designed to reproduce using local materials in other star systems, remain constrained by temporal limits. A wave of such probes, spreading at 10% of light speed, would require approximately 1 million years to traverse the galaxy. This duration of 1 million years exceeds the lifespan of nearly every complex species known. Civilizations rise and fall in much shorter intervals, meaning the probes might complete their mission long after their creators have become extinct. Throughout this entire process, entropy continues. The second law of thermodynamics ensures that order degrades into disorder. Over time, no structure maintains perfect stability indefinitely. Biological systems accumulate mutations, and mechanical systems accumulate wear. Information storage degrades unless it is constantly refreshed. Interstellar travel is not merely a question of reaching a destination. It is a commitment to preserving order against entropy for durations that vastly overshadow recorded history. Distance sets the scale. Energy sets the cost, and time determines whether the effort can remain coherent. For a sufficient period to matter, a civilization capable of venturing into stellar space must not only master propulsion, but also sustain its purpose across centuries, maintain mechanical integrity across millennia, and survive cultural transformation without losing the initial reason for embarking on the journey. The longer the trip, the more fragile that continuity becomes. Time does not obstruct interstellar travel in a dramatic fashion. It neither causes ships to explode nor engines to fail. It simply prolongs the journey until civilizations, their machines, and their intentions unravel under its immense pressure. Even if a civilization overcomes distance and pays the energy cost, and commits to enduring the passage of time, one problem persists before the journey even commences. They must ascertain their destination from an interstellar distance. Earth does not appear as a distinct blue marble suspended in space. It does not visibly exhibit life, nor does it broadcast an inhabited beacon. It is merely a small, rocky planet orbiting an ordinary star. The Sun, one among approximately 400 billion stars in the Milky Way, is neither remarkably large nor particularly luminous when viewed from hundreds or thousands of light-years distant. It merges seamlessly into a crowded expanse of comparable stars, possessing no distinguishing features that would draw notice. Directly identifying Earth, even from just a few light-years distance, necessitates exceptionally precise equipment. With an approximate diameter of 8,000 miles, our planet appears as a minuscule dot next to the Sun, reflecting only a tiny portion of the star's illumination. To discern a small planet from hundreds of light-years away would demand telescopes equipped with apertures spanning hundreds of kilometers. Furthermore, what would be visible? They would observe Earth as it existed at the moment the light departed. Should a civilization be situated 1,000 light-years distant, the light arriving at their devices this evening originated from Earth a millennium ago. They would perceive the planet as it was during the medieval era, devoid of radio transmissions, satellites, or industrial contamination. No discernible urban illumination would be detectable at such a range. Instead, they would observe a terrestrial world featuring an atmosphere abundant in oxygen, which implies biological processes. However, this does not assure the presence of intelligent beings. Numerous planets might exhibit atmospheric compositions resulting from microbial ecosystems. To dedicate millennia and vast energy reserves to journey to a world solely on the basis of its atmospheric oxygen would demand exceptional conviction that something unparalleled awaits discovery. Earth lacks obvious distant uniqueness. Our radio transmissions have been escaping into space for approximately a century, signifying that these signals have traversed roughly 100 light-years in all directions, creating a detectable sphere 200 light-years in diameter. While this may sound vast, it is not. The Milky Way extends for approximately 100,000 light-years. Our radiosphere occupies only a minuscule portion of its total volume. A civilization located 1,000 light-years away has not, as of yet, detected any indication of our technological presence. Even upon their arrival, these signals will be extremely weak, as electromagnetic radiation adheres to the inverse square law. When a signal propagates outwards, its intensity diminishes proportionally to the square of the distance. If the distance is doubled, the signal's strength reduces by a factor of 4. Multiply the distance by 10, and it weakens 100-fold. By the point an Earth broadcast has journeyed hundreds of light-years, its energy will have dispersed across an immense spherical area. Differentiating it from the ambient cosmic background noise becomes exceptionally challenging. Natural radio emissions originating from stars, pulsars, and various other astrophysical phenomena permeate the galaxy. Our transmissions must contend with this background, meaning detection is not assured. Let us now revisit the scale. Should intelligent civilizations be uncommon, perhaps appearing once every 10 million stars, then the closest one could be situated thousands of light-years distant. Their equipment would be required to discern a subtle oxygen signature from Earth's atmosphere across that vast expanse prior to our radio transmissions ever reaching them. Even if intelligent civilizations are more prevalent, separated by merely a few hundred light-years, the challenge of detection persists. A few hundred light-years still represents a considerable distance. From that vantage point, Earth looks like a faint dot beside a typical star. For them, the galaxy holds millions of possibly life-sustaining worlds. Numerous such planets might display intriguing atmospheric indicators. So why select our world? As previously noted, journeys between stars represent endeavors spanning millennia with immense energy demands. No society would undertake such an expedition lightly. The destination must warrant the outlay. However, Earth doesn't overtly signal its presence. Even sophisticated observational methods like the transit technique, which spots a star's minor obscuration, when a celestial body crosses its path, rely on precise geometric positioning. Only viewers situated within Earth's orbital plane would witness our world passing before the Sun. From the majority of galactic locations, such an alignment won't happen if their viewing angle doesn't cross our planet's orbital path. Our world would never obscure the Sun from their perspective. Thus, the planet stays concealed. One could contend that a highly developed society might meticulously chart every stellar system. Conceivably, they could deploy extensive telescope networks or interferometers able to discern far-off planetary terrains. Even so, clarity diminishes with range. To distinguish details on Earth from a distance of 1,000 light-years would necessitate an instrument opening thousands of kilometers wide. Building such a device constitutes an engineering feat on a megastructure scale. And what would be their reward? A dim picture of a minor planet circling an average star. No clear indicator unequivocally signals an advanced civilization over such vast spans. Atmospheric industrial contaminants are mere trace elements next to oxygen and nitrogen. The nighttime glow from urban areas is exceedingly dim compared to reflected starlight. From an interstellar distance, Earth doesn't radiate with signs of intellect. Let's now flip the viewpoint. In recent decades, we found thousands of exoplanets, with many situated in their stars' life-sustaining regions. A few exhibit atmospheric indicators aligning with water vapor or potential biosignatures. Yet, we don't dispatch starships in their direction. Even if we verify microscopic life on a world 50 light-years distant, the expense of physically journeying there stays excessive. A society assessing Earth would confront an identical computation. The separation is immense. The power required is colossal. The duration spans centuries or millennia, and the objective is ambiguous. Undertaking an expedition, given those circumstances, demands a powerful motive. Mere inquisitiveness might not warrant an investment spanning multiple millennia. Furthermore, stellar movement presents an issue. Stars aren't static, they revolve around the galactic core at hundreds of kilometers per second, causing their locations to change over millennia. A stellar system aimed at today won't be found at the identical coordinates centuries hence. Precise, extended trajectory planning needs to factor in star movement, gravitational disturbances, and accumulated navigation inaccuracies. A minor error in calculation upon departure could lead to missing the intended system. After journeys spanning millennia and billions of miles, navigating through interstellar space necessitates exceptional accuracy. Interstellar space lacks navigational markers. No gravitational anchors exist beyond remote stars. Adjusting course demands more energy, which in turn necessitates more fuel. Furthermore, as a spacecraft nears relativistic velocities, even minute particles grow increasingly destructive, a solitary dust grain. When striking at a fraction of light's velocity, is capable of unleashing explosive amounts of kinetic energy. Shielding contributes mass, and increased mass elevates energy consumption. All these endeavors would be aimed at a world that might or might not harbor intelligent life upon the vessel's arrival. Since life evolves, a civilization observed from 1,000 light-years away would be perceived as it existed a millennium prior. Should they travel at 10% of light speed, the voyagers would reach their destination 10,000 years later, by which time the initial civilization could have undergone significant transformation. to an unrecognizable state or vanished entirely. The objective is not fixed. The galaxy itself is in constant flux. Stars migrate, planets develop, and civilizations emerge and decline. Any extraterrestrial species contemplating a voyage to Earth would need to assess partial data concerning a far-off planet. They would have to consent to immense energy outlays, withstand thousands of years of transit, and land in an unforeseeable future, all without any assurance that the ultimate goal warrants such an expense. Interstellar journeys bear no resemblance to exploring a close island with discernible coastlines. Instead, it's akin to embarking across an ocean, heading for a signal that might no longer exist. This represents the ultimate barrier before traversing the emptiness. Prior to achieving relativistic velocities, and before maintaining a society for centuries, they must first ascertain that Earth merits a visit. From the majority of the galaxy, we are not discernible from even a handful of viewpoints. We are virtually undetectable. Are we sufficiently captivating to warrant a voyage spanning millennia? The cosmos not only divides civilizations through vastness and energy, but also conceals them from each other. Here a frequent observation arises: the distances are immense. The energy demands are exorbitant, and the temporal spans are staggering. However, perhaps our perspective is too limited. Conceivably, a highly developed civilization would not endeavor to creep between stars at a mere fraction of light's velocity. Instead, they might circumvent the issue altogether, employing concepts like warp drives or wormholes. Travel exceeding light speed, these notions are well known from speculative fiction, yet they also possess foundations in theoretical physics. The query remains whether they constitute genuine answers, or merely theoretical oddities that fail when subjected to rigorous physical examination. Let's begin with light's velocity itself. As per special relativity, the velocity of light in empty space is more than just a rapid pace. It constitutes a fundamental characteristic of space-time. It signifies the ultimate speed at which data or physical substance can move. When an object possessing mass accelerates towards light speed, its relativistic mass grows with every subsequent increase in velocity. The energy needed surpasses that of the prior instance. This energy demand doesn't escalate linearly, but rather asymptotically. Precisely at light speed, the necessary energy becomes boundless. Achieving infinite energy isn't just a major engineering hurdle, it's a physical impossibility. No degree of technological advancement permits any civilization to create it. This boundary of infinite energy has been put to the test numerous times. Particle accelerators propel subatomic particles to velocities that are exceedingly close to the speed of light. As these particles draw near that threshold, the energy necessary to accelerate them further escalates dramatically, precisely as predicted by the theory of relativity. The governing equations do not yield. The speed of light isn't a constraint imposed by contemporary technology. Rather, it's intrinsically woven into the geometry of spacetime. To journey faster than light, one would be required to bypass this geometric constraint. A proposed method is the Alcubierre warp drive, conceptualized by physicist Miguel Alcubierre in 1994. This concept does not involve moving a spacecraft through space at speeds exceeding that of light. Instead, it suggests compressing the space ahead of the craft while expanding it behind, thereby forming a warp bubble that propels the vessel forward. In theory, the ship within this bubble never locally surpasses the speed of light. Space itself is performing the movement. The mathematical solutions are valid within the framework of general relativity, but the physical demands are stringent. A warp drive requires exotic matter, specifically material with negative energy density that exerts gravitational repulsion instead of attraction. No such substance has ever been observed in quantities that could be utilized. Negative energy manifests in minor, transient quantum effects, but nothing even remotely approaches the stable, large-scale forms necessary to maintain a warp bubble. Initial calculations indicated that generating a warp field would demand energy equivalent to the mass energy of the entire observable universe. Subsequent refinements dramatically lowered this estimate, yet only to levels comparable to the mass energy of a planet like Jupiter. If it were entirely converted into energy, This is not an engineering challenge. It represents a fundamental absence of physical feasibility. Wormholes, or Einstein-Rosen bridges, present another theoretical shortcut. In theory, a wormhole links two distant points in spacetime via a tunnel-like structure. Passage through such a structure could be almost instantaneous, irrespective of the external distance. However, stable, traversable. Wormholes encounter the same impediment as warp drives. They necessitate exotic matter to remain open. Without negative energy density to counteract gravitational collapse, the wormhole would pinch shut more rapidly than anything could pass through it. Furthermore, wormholes introduce issues concerning causality. Superluminal travel, when combined with relativity, has the potential to generate time paradoxes, enabling effects to precede their causes in certain reference frames. Many physicists hypothesize that fundamental laws, sometimes referred to as chronology protection, prevent such paradoxes from occurring. In other words, the universe may prohibit stable wormholes. Given that they would contradict consistent cause and effect relationships, no empirical proof for traversable wormholes has been discovered. Neither astronomical observations have unveiled a natural one, nor have laboratory experiments indicated controllable negative energy in the necessary configuration. Quantum entanglement offers a different concept. Particles in an entangled state demonstrate correlations over distance that seem instantaneous. Some theorize this could allow for communication beyond the speed of light. Nevertheless, entanglement does not convey practical information faster than light. The statistical results observed still demand classical communication. For the purpose of comparing results, relativity remains robust. Every proposed loophole eventually confronts the identical limitation. It either necessitates forms of matter never witnessed in nature, or it infringes upon causality, or it demands energy scales surpassing any realistic physical interpretation. The fascination with faster-than-light travel exists in imagination. The limitations originate from experimentation. Relativity is not a delicate theory on the verge of collapse. It has withstood over a century of progressively precise examinations. Time dilation has been quantified using atomic clocks, and gravitational waves have been observed. GPS satellites are required to factor in relativistic adjustments for proper functioning. The speed of light's upper bound is intrinsically integrated into every confirmed prediction of modern physics. To overturn it would necessitate rewriting more than just a single equation, but rather the entire framework of space-time. Could future discoveries broaden our understanding? Possibly. Science is always receptive to revision, but speculation about unknown physics cannot function as a practical conduit across light years. An advanced civilization does not gain immunity from physical law simply by virtue of its advancement. A species millions of years older than humanity still resides within the identical space-time geometry. It continues to abide by the conservation of energy and still experiences entropy. Greater knowledge might enable more efficient propulsion. It cannot nullify relativistic constraints, even for a civilization harnessing the full energy output of its star. A so-called Type 2 civilization would still encounter the identical limit. More energy permits additional attempts. It does not enable infinite acceleration. A Type 3 civilization, utilizing the energy of an entire galaxy, would still be restricted by the same light speed ceiling. Power does not modify geometry. If faster-than-light travel were physically feasible, in a stable, manageable form, the universe itself would appear different. We would anticipate seeing evidence of rapid galactic colonization, including signals, structures or anomalies that are inconsistent with slow expansion. Instead, the cosmos appears tranquil. The absence of obvious galaxy-spanning activity implies either that civilizations are uncommon or that faster-than-light travel is unavailable to them. Physics does not guarantee convenience. It guarantees consistency. The coherence of relativity, validated across scales from laboratory experiments to astrophysical observations, indicates interstellar journeys are confined to sublight speeds. Any sublight travel reintroduces all previously mentioned obstacles, making distances immense. Energy requirements become immense, and time takes precedence. Without shortcuts exceeding light speed, the galaxy's vastness remains unchanged. Every star stays separated by light years of empty space, and every civilization is limited by the identical universal structure. The aspiration of easy interstellar journeys hinges on altering the fundamental principles governing space and time. Yet these laws have displayed no indication of bending. The velocity of light isn't a technological hurdle, awaiting a breakthrough. Rather, it's an inherent characteristic of the cosmos, and while it persists, every civilization, regardless of its intellect, is compelled to operate within its limits. If distances extend beyond what's intuitive, if energy needs surpass what's feasible, and if time degrades each mission well before its destination is reached, a more significant inference starts to emerge. The inquiry changes from, are they present, to, even if they exist, is it truly possible for any two civilizations to ever genuinely encounter each other? Our galaxy, the Milky Way, is approximately 13 billion years old. Throughout this immense period, stars have undergone cycles of birth, life, and death. Planets have cooled, and intricate chemical processes have developed. On at least one planet, Earth, intelligence arose. There's no clear justification to assume Earth is the sole location where this phenomenon took place. Considering the vast quantity of stars and the widespread existence of planets, it's conceivable that life has originated on numerous occasions, and it's equally plausible that intelligence has appeared multiple times. Whole civilizations might have thrived millions of years prior to humanity's development. Others could emerge long after our disappearance. However, the galaxy isn't merely expansive in its spatial dimension. It is also immense across time. Civilizations are not eternal. Human technological society has only been present for a few hundred years, and even if it persists for several millennia longer, that duration is minuscule when set against the entirety of galactic history. A civilization might thrive for 10 millennia, an exceptional accomplishment, and subsequently diminish, break apart, or evolve into an unrecognizable form. Now imagine two civilizations separated by 1,000 light years. Even if both attain the capacity for interstellar travel, their periods of viability need to coincide. They must be contemporaneous, and both must possess the inclination and the means to initiate communication. Our galaxy encompasses hundreds of billions of stars, distributed over a span of 100,000 light years. If civilizations are uncommon, with thousands of light years between them, the likelihood of two such societies emerging concurrently and endeavoring to connect with each other diminishes. If civilizations are prevalent, separated by merely hundreds of light years, the time lag for communication still extends for centuries, and travel durations span millennia. Civilizations might emerge and vanish without ever becoming aware of their neighbor's existence. This concept reinterprets the cosmic silence. The lack of extraterrestrial visitors doesn't necessarily imply that intelligent life is scarce. It could simply indicate that the universe's inherent structure mandates isolation. Every star system resembles an island within an immense cosmic ocean. On Earth, islands divided by oceans can ultimately establish connections via ships and airplanes. While Earth's oceans are finite and can be traversed within a human lifespan, the interstellar ocean stands apart, its vastness measured in light years. This undertaking necessitates energy on a planetary scale and dictates travel durations that exceed the lifespan of civilizations, even if a society develops self-replicating probes. These machines, which create copies of themselves and propagate outwards, form an expansion front that advances slowly compared to galactic dimensions, even at 10% of light speed. To traverse the Milky Way requires approximately 1 million years, a time frame extensive enough for continents to shift and climates to change, and for species to evolve or vanish. The civilization that launched the initial probe would not recognize the galaxy by the time the final probe reached the opposite edge. Time effectively decouples cause and effect. Across interstellar space, the question of motivation also arises. Exploration demands a clear purpose, meaning a civilization must decide that the energy cost, time, and risk is justified. This calculation depends on its values, priorities, and internal stability. Not every society pursues maximal expansion. Some may focus internally, Others might transition into digital or virtual forms, thereby reducing the incentive to colonize physical worlds, and some may conclude that the risks outweigh the benefits. Interstellar expansion is not an automatic outcome of intelligence, it is a deliberate choice, and that choice must persist across centuries of political and cultural change. The laws of thermodynamics introduce an additional constraint. Entropy ensures that maintaining order requires continuous energy input, compelling civilizations to invest resources, simply to preserve themselves. Infrastructure, climate control, and ecological balance all demand energy, making the diversion of enormous power toward interstellar ventures. Competes with domestic stability. Over time, internal pressures may come to outweigh distant ambitions. The more advanced a civilization becomes, the more complex its systems become. This complexity increases vulnerability. A single cascading failure, ecological, technological, or social, can destabilize the entire structure. If the lifespan of advanced technological societies is limited by self-inflicted risks or natural hazards, their interstellar window may be brief. Combine short civilizational lifespans with vast spatial separation, and the galaxy becomes a collection of isolated episodes rather than a connected network. There is a tendency to imagine a mature galaxy filled with star-spanning empires, continuous communication, and coordinated expansion. However, that image assumes that physics allows rapid, sustainable movement between stars. If it does not, the default state is fragmentation, where each civilization illuminates its own system for a time, then fades. The light from that civilization, in the form of radio signals or atmospheric changes, spreads outward at the speed of light, but by the time it reaches distant stars,